All right, thank you very much. It's great to be here and have a chance to share with you a little bit about our new research center. I'm a professor in School of Communication Sciences and Disorders and director of the new Communication Technologies Research Center. I joined UCF this past fall, so we're just launching the center. My background, I have a master's degree in clinical audiology, which is the profession that deals with hearing loss. I'm a scientist and a Ph.D. in sensory psychology. And partner with lots of engineers in my research and translational work, and hope to continue to do that here at UCF. So we're starting this research center from scratch and hope that we can develop a hub for innovation, discovery, exploration, and translation. And at least starting out, our main focal areas are hearing science, speech science, voice science, aging and cognition, balance, and related areas. And one of our important goals is to have partnerships that support rapid advancement from concept to practice, including implementing projects quickly so that we can be conducive to industry funding. So we're shooting to diversify our faculty, our funding, and projects. And the faculty that we've hired so far, most of whom are joining us over the summer, are hearing scientists, speech scientists, voice scientists, neuroscientists, electrical engineering, backgrounds in biomedical engineering, mathematics, acoustics. And one piece we're missing at the moment is data science. So we are certainly looking for collaborators at that level. Our core, we have basically 4 divisions of the center at the moment: hearing technologies division, an auditory neuroscience division, a voice and upper airway division, and a simulation and virtualization division. And most of our funding right now is from either NIH or NSF. We are targeting some DoD funding, and we have a number of corporate partners that we work with. We have some world-class facilities that the UCF administration has been so kind to provide for us, and they actually started building this before I came to UCF, which is remarkable in and of itself. So this is in Research Park on Progress Drive in a building called the Innovation Center. And this is where the university's Human Resources Department was prior to our taking over this space. The center space here is some of the primary research space. It's about 3,000 square feet. And we have 6 of these sound attenuating chambers dedicated to different functions. But these are double-walled sound enclosures that attenuate sound produced in the chamber from coming out and attenuate sound outside the chamber from coming in. And we have a variety of different research setups in these chambers. We also have a larger one over in the lower left of this space. It's a sound booth that is 13 feet by 13 feet by 11 feet high. And we're constructing an 86 speaker array to simulate various communication scenarios and other environmental situations for human subject participation and also device evaluation. And then we have the live lab down at the bottom, which is under construction now, but basically a very large sound attenuating room, vibration isolated from the building itself in multiple ways, and configurable so that we can tune the acoustics of the room from being extremely reverberant to extremely dry and anywhere in between, and large enough to engage multiple people at the same time in different communication activities, wearing different assistive technology devices, having different sensors on them, camera technologies in there as well, so we can really learn more about the function of devices and people together. And then what you don't see, we also have office space around the perimeter, and we're just about to break ground on a separate building just below the live lab here to house an anechoic chamber for human testing. And that will allow us to get at the ground truth for auditory perception, to test devices when there aren't reflections in the room, and also a real base for virtualization and simulation using audio. So we have so far hired 5 tenure track faculty, 5 research professors, and we're recruiting clinical experts and administrative support at the moment. So I'm going to give you just an example of several projects that we work on. One is a novel treatment for hyperacusis, and this was an NIH-funded grant that was sort of a seed grant on R21. Hyperacusis is an unusual intolerance to the loudness of ordinary environmental sounds. So people who suffer from this condition have a real difficult time interacting with the world around them because they perceive many sounds that are natural to us as being debilitatingly uncomfortable. One of the problems is it's a very low prevalence disorder, but it has a devastating impact, most often causing either a change of career or a loss of career. There are evidence-based treatments. It usually involves some combination of sound therapy and counseling. However, there's some huge barriers to success of those treatments, one of which is self-treatment using earplugs to prevent exposure to high-level sounds, but it's extremely counterproductive and actually exacerbates the loudness tolerance condition. And so it makes it very difficult to wean people off of these devices and translate them into therapy devices. And so the solution that we've come up with and patented is a novel device that consists of a very good earplug connected to essentially the guts of a hearing aid. So we chose a chipset that emulates a lot of hearing aid technology from ON Semiconductor. We selected MEMS mics and high quality receivers and packaged them with an earpiece that has a heat activated stent. So when that gets inserted into the ear and gets up to body temperature, it expands and gives us a really, really good earplug. And then with the onboard signal processing, we can adjust gain from ear plugging up to unity gain and overcome that ear plugging, making it a transparent device. And then provide sound therapy, which is low-level, sort of seashell-like noise, which expands dynamic range over time. And that also allows the wearer to get healthy exposure to lower-level sounds. And then we use amplitude compression technology to limit exposure to high-level sounds. And in the first trial of this device, we increased sound tolerance in a group of 12 individuals on average by 35 decibels. And given that our loudness dynamic range with normal hearing is only about 100 or 110 decibels, this is a huge change. And so very successful, but we still have barriers to implementation. And one of those is this low prevalence of the disorder. So low that most major manufacturers of hearing technologies aren't interested in investing the funds to produce custom devices for this population. So with this nail, our hammer, our solution is to find a new nail. And one of those is the sound sensitivity disorder suffered by approximately 60% of people who have autism spectrum disorder. And so we believe that this technology will help people who have a milder form of the same disorder and comorbid autism spectrum disorder. So we have a number of funding sources that we will be looking towards, including a defense contract, a defense organization in an NIH for a Small Business Innovative Research Award and a multi-site clinical trial. So that gives you a little bit of idea of some of the type of work we do. This second project goes in a different direction. It's accessible assessment of respiratory function. I think I spelled that incorrectly. But for a voice evaluation in the world of speech language pathology, it's mandatory to do an upper airway assessment. But in many cases, those assessments are not done because of poor accessibility. The hardware is cumbersome to use. It's expensive at medical grade technology, and the software is inconvenient and not blended with software that the professional is already using. And so what we've done is developed a low-cost, accessible solution to this problem, which is a whistle. That combined that with an app and a unique distribution model, we think we can solve the accessibility and cost issues related to lack of use in this field, and then expand the use of this technology into many other fields dealing with respiratory function. And so our solution is a simple whistle, and I'm holding one up now in front of the camera if you see that image, 3D printed in this version. And you can see through our partners in mechanical engineering, they've done flow modeling, and you can see the vortex that is created when you expire into or blow into the whistle. And then a sound comes out of the whistle produced by that vortex, and the frequency of that sound, at least the primary harmonic that comes out, is directly proportional to instantaneous airflow. So we essentially have no moving parts system for measuring instantaneous airflow. And if you accumulate that over time, then you get a measure of vital capacity. assuming a deep inhale and a full expiration. And so this is just a show of a flow diagram that we would integrate across to get vital capacity. On the y-axis of this graph is estimated lung volume using a $5,000 clinical system called a COCO. And on the x-axis, what we get with the Vortex whistle that costs pennies to produce and using a smartphone app. And our partners also have helped us develop a test jig for evaluating different modifications of the whistles. So this is essentially syringes that force air through a manifold and into the whistle. It's then recorded by a microphone, and we just have a simple Arduino controller activating the linear actuator and controlling the movement of that to systematically control airflow. We want to commercialize this. So one of our next app, we have an R01 that just started in September. So that's a 5-year, $3 million grant. We want to pursue a small business innovative research grant to move this towards commercialization and then get into more medical aspects of respiratory function with this technology. And then the third project that I want to highlight for a second, excuse me, is the impact of hearing technology on communicative and cognitive function. And so it's pretty well known that untreated hearing loss and the associated perceptual difficulties impact communicative function, but they also impact cognitive function and lead to cognitive decline and a whole host of other risks for health failure. And one of the tricks we have is very, very difficult on an individual basis to demonstrate that hearing aids improve cognitive function. One of the reasons is that the measures you typically use are very sparse. They're acute. You do it once, maybe before a study and after a study, and look for change. And so our solution is to use a technique called ecological momentary assessment. And we assess cognitive function through smartphone apps that are gamified and take about 3 minutes to estimate cognitive function on 3 or 4 different cognitive domains. And then we have some survey questions that tell us about the acoustic environment and communication scenario, and can connect the hearing devices to get acoustic measures from those as well. With the notion that with this, we get a high density of data under different circumstances and can start to think about variability in function and minimizing that variability with treatment, and hopefully have greater sensitivity to disease progression and treatment-induced change. And with that, we hope to secure an NIH R01 and then move this technology into a consumer-based product as well. So with that, I'd love to hear any comments or questions that you may have.